Why do things stop behaving like things the smaller we look? It's a question that feels almost mischievous, as though nature hid a secret beneath every layer of existence, waiting for us to peel it back. At vast scales, the universe appears steady and predictable. Stars orbit, planets drift, galaxies gather. Yet the moment we shrink our lens below the familiar, reality begins to shimmer, twist and loosen its grip on anything we might call normal. It's as if the universe is perfectly comfortable being understandable until you ask too many questions. Tonight, you're in a quiet place where the rhythm of your own breath softens the edges of thought. Imagine the room dim, the world slowed, the noise of the day fading into a gentle hum. Here, curiosity doesn't burden the mind, it relaxes it. This calm space allows you to wander freely through the smallest realms imaginable, without fear, without urgency, just drifting through ideas as softly as dust floating through a beam of moonlight. As we descend into the microscopic and the submicroscopic, something remarkable happens. The rules that govern your everyday experience begin to dissolve. Particles stop behaving like solid objects and start acting like whispers, probabilities and waves of possibility. Classical logic, so dependable at normal scales, struggles to hold on. Instead, a new kind of truth emerges, one shaped by uncertainty, symmetry, and the delicate fabric of quantum fields. Understanding this isn't merely scientific, it's profoundly human, because it reveals how limited our intuitive senses truly are. If these calm explorations help you unwind, or give you a soft place to end the day, feel free to leave a like and subscribe to the channel. It gently helps others find their way to this quiet corner of the universe, where curiosity slows down and the mind can breathe. Now let's begin slipping beneath the world you know, past molecules, past atoms, past even the particles you've heard of, into a realm where reality becomes uncertain, beautiful, and deeply strange. At everyday scales, the universe feels sturdy. Objects stay where you leave them. Time moves forward at a comfortable pace, and causes led to effects with a reliable sense of dignity. This stability isn't just comforting, it's foundational to how your brain interprets the world. You rarely question whether a chair will remain a chair or whether a dropped glass will fall instead of float. The macroscopic world behaves politely, but this politeness is a kind of illusion, maintained only because you're watching from far, far above the true machinery. Physicists began noticing hints of something unusual in the late 19th century. Light didn't always act like the waves they expected. Energy sometimes arrived in discrete packets, refusing to behave like a smooth, continuous flow. Atoms emitted radiation in sharp steps rather than gentle gradients, and electrons, instead of orbiting like planets around a star, appeared to leap between energy states as though teleporting. These observations weren't errors, they were clues that the universe obeyed a deeper, more intricate rulebook at small scales. There is a delicate image that helps frame this transition. Picture reality as a vast ocean at night, calm on the surface, predictable, gently shifting with the tides. But just beneath, the water churns with vortices, currents, and flickers of turbulence. From a distance, the sea looks serene. Up close, it becomes a restless storm of motion. The microscopic world works the same way. Stillness dissolves into activity, solidity dissolves into vibration, certainty dissolves into possibility. This realization carries an unsettling but wondrous implication. What you consider normal is simply what happens when trillions of chaotic interactions average out. The classical world is not fundamental. It's emergent, born from deeper structures that do not resemble the world you see. And in that recognition, a kind of philosophical humility emerges. Your intuition is not the measure of truth. It's just a survival tool shaped for a middle-sized realm. When researchers probed smaller scales, they discovered that particles didn't have definite positions unless measured. They existed in clouds of probability, meaning they occupied many possible states simultaneously. The equations describing them, wave functions, didn't tell you where a particle was, only where it might be. At first, this sounded absurd, but experiments repeatedly confirmed it. The microscopic world doesn't commit to a single outcome until observation forces it to do so. A strange analogy softens this idea. Think of a faint melody drifting from another room. You sense its presence, but its exact notes blur together until you step closer. The melody exists, but not with precision. It's more like a suggestion, a haze of possibilities. Particles behave similarly. They exist, but not in the crisp edges your intuition demands. Their reality is more like potential than presence. The philosophical echo of this discovery is profound. If the fundamental components of nature behave as waves of possibility, then certainty, the thing humans cling to for comfort, may be a luxury afforded only at large scales. The universe might not be committed to specifics until interaction forces its hand, and perhaps your own life mirrors this. Paths remain open until choice collapses them. Quantum behavior becomes even more unusual when you consider duality. Experiments showed that particles like electrons and photons behave as both waves and particles, switching depending on how they're observed. They move like ripples across space, yet strike detectors like tiny marbles. This dual identity isn't a trick. It's built into the fabric of the universe. Even the famous double-slit experiment demonstrated that observation itself alters the outcome. Reality is sensitive, reactive, and deeply contextual. An evocative image helps hold this idea. Imagine a lantern in dense fog. The light spreads, diffuses, fills the air in a soft cloud, just like a wave. But toss a pebble into that fog, and you feel something solid strike your hand, just like a particle. Light lives in both worlds, shifting its behavior depending on how it's asked to reveal itself. Philosophically, this duality challenges the human desire for clean categories. People want things to be one thing or another, wave or particle, definite or uncertain here or there. But nature resists such binaries. It prefers a softer truth. Identities can be plural, contextual, fluid. Perhaps the universe is teaching something about flexibility, about embracing complexity rather than forcing simplicity where it doesn't belong. Further down the scale, atom models revealed another oddity. Electrons do not orbit nuclei like miniature planets. They exist as standing waves, smeared across regions of space in patterns called orbitals. These shapes, clouds of probability, are not guesses. They're mathematically precise, confirmed by spectroscopy and quantum chemistry. The atom is not a tidy solar system. It's a symphony of vibrating fields. A poetic metaphor frames this beautifully. Think of a violin string vibrating in many harmonics at once. Each mode contributes to the overall character of the sound. Electrons, too, live as harmonics of the quantum fields they inhabit, each configuration shaping the atom's personality. They are less like beads and more like musical notes. Reflecting on this changes how one sees the world. The chair beneath you, the screen glowing in front of you, the air drifting across your skin, all of it is built from ghost-like waves of possibility that only appear solid because your senses smooth them out. Solidity is a perception, not a fundamental property. The universe is far stranger, far softer than your everyday experience suggests. As quantum mechanics matured, scientists discovered that particles can tunnel through barriers they seemingly have no energy to cross. This tunneling effect is not hypothetical. It powers nuclear fusion inside the sun and enables modern electronics. A particle doesn't march over a barrier. It slips through it, as though reality itself has a hidden back door. The imagery of a bird passing effortlessly through fog captures the essence of tunneling. The barrier is present, but not absolute. The particle doesn't break it. It bypasses it with grace, gliding into a space it had no classical right to enter. At small scales, the rules soften, loosen, and become pliable. Philosophically, this reveals a universe where impossibility is sometimes an illusion. The boundaries you perceive in life, obstacles that seem impenetrable, may not be as rigid as they appear. Scale them down far enough, and even the impossible gains a tiny doorway. Superposition introduced another leap in strangeness. A quantum system can exist in multiple states simultaneously until measured. A particle can spin both up and down, occupy two locations, or pass through both slits at once. This isn't metaphorical. It's been demonstrated in laboratories countless times. Even large molecules have exhibited superposition, pushing the limits of how far quantum weirdness can extend. Visualize a path winding through a forest at twilight. In the fading light, the trail seems to split, shimmer, and overlap depending on where you stand. It's still one path, but its possibilities overlap in your perception. Superposition resembles that. Many states coexisting, woven together until interaction clarifies which branch becomes real. The philosophical takeaway is subtle. Life often offers many versions of you, many potentials, many futures intertwined until choice crystallizes one. Perhaps the quantum world reflects that same structure, a universe built from intertwined possibilities, waiting for small acts of attention to define the next step. Entanglement pushed the boundary even further. Two particles can become so deeply linked that the state of one instantly influences the other, no matter how far apart they are. Einstein famously called it spooky action at a distance, but experiments have shown it to be real. This phenomenon sits at the heart of quantum communication and emerging quantum computers. A gentle image helps hold this idea. Imagine two leaves drifting on a vast pond. A ripple touches one leaf, and instantly the other responds, not through space, but through a hidden unity in the water beneath. Entangled particles share that kind of secret connection, bound not by distance, but by a shared quantum story. Reflecting on entanglement introduces a softer, more human idea that separation is sometimes an illusion. Connections can remain even across immense space, even across time. The universe, at its smallest scales, hints that relationship is fundamental. Measurements showed another twist. Observing a quantum system changes its behavior. This isn't mystical, it's a consequence of interaction. To measure a particle, you must disturb it, collapsing its wave function into a definite state. The act of knowing becomes part of the phenomenon itself. Think of brushing your hand through water. The moment you touch it, the surface shifts, ripples, rearranges. You can't observe it without altering it. Quantum measurements behave exactly like that. The observer becomes woven into the event. This realization provokes a philosophical question. How much of reality is shaped by participation? In the quantum world, observation is not passive, it is part of the story. Maybe awareness plays a deeper role in existence than you intuitively imagine. When all these discoveries are gathered together, a remarkable picture emerges. Classical reality, the world of certainty, is not the foundation of existence. It is a shadow cast by deeper rules, rules written in probabilities, vibrations, and relationships. And as you peer downward into smaller and smaller realms, those shadows begin to break apart. This descent into the subatomic reveals the first cracks in the reality you know. Certainty loosens, identity softens, boundaries blur. The familiar dissolves into a shimmering field of mathematical possibility, and as you drift downward, the strangeness only intensifies, inviting you further into the depths. At human scales, reality carries the soothing illusion of smoothness. Movements flow without interruption, objects seem whole, and time unfurls in one unbroken ribbon. You lift a hand, and it rises effortlessly, as though the world beneath it were continuous. This sensation tricks the mind into believing that nature is built from unbroken lines and seamless surfaces. But the deeper science reached, the more cracks appeared in this comforting picture, revealing a world composed not of continuities, but of quantized steps. Physicists realized early in the 20th century that energy is not a gentle gradient, but a staircase. Electrons absorb and emit photons only in discrete amounts, quanta, never in between. It's as if the universe forbids half steps. This discovery reshaped every field of physics and marked the beginning of quantum theory. What appears smooth at your scale hides an architecture of increments so tiny they evade intuition. Yet the existence of these steps is undeniable, confirmed through spectroscopy, lasers, and the very electronics powering your device. It helps to imagine a lantern illuminating a misty room. From afar, the glow seems continuous, soft, uninterrupted. But as you approach, you notice the faint granularity of dust motes drifting through the beam. They catch the light in tiny flashes, like discrete beats of brightness. The glow feels smooth only when viewed from a distance. On close inspection, it's a mosaic. Reality behaves just the same, seamless from afar, quantized up close. Realizing this challenges the human instinct for continuity. People want stories to progress smoothly and growth to follow predictable curves. Yet, even in life, changes often come in jumps, moments of insight, sudden decisions, abrupt shifts. Perhaps the quantum world is not so alien after all. It echoes patterns that appear in your own experiences. Momentum, too, is quantized. In confined spaces, particles can only occupy specific modes of motion. Electrons within atoms vibrate in standing wave patterns, each with its own allowed energy. They cannot simply choose any level they wish. Their existence is a negotiation with the geometry that contains them. This isn't speculation. It's observed in atomic spectra and forms the basis of chemical bonding. To see this more gently, envision a drum in a quiet hall. When struck, it doesn't produce every conceivable sound. It resonates at specific frequencies determined by its shape and tension. The empty air around it seems infinite, yet the instrument allows only certain notes. Particles behave the same way, resonating in allowed modes defined by the spaces they inhabit. Philosophically, this suggests that freedom isn't unlimited. It unfolds within constraints. But constraints don't diminish beauty, they shape it. A melody owes its character to the notes it cannot play. The quantum world mirrors this. Its structure arises from limitation, not in spite of it. Time adds another twist. At small scales, events do not necessarily unfold in the orderly linear way you experience. Quantum transitions can occur abruptly, with no smooth travel between states. A particle doesn't slide from one energy level to the next. It jumps. This concept, once ridiculed, is now central to physics. Even radioactive decay is governed by probabilistic timing, not a fixed schedule. Picture a candle flickering in a dark room. Its flame burns steadily, yet occasionally, without warning, it leaps, brightens, or dims. The change is sudden, unpredictable, almost whimsical. Quantum transitions possess that same quality, abrupt and unannounced, governed not by certainty but by probability. The philosophical resonance is clear. Change often arrives without gradual build-up. One moment feels like the last. and then suddenly everything is different. The microscopic world seems to whisper that unpredictability is woven into the universe's foundation. Experiments revealed another counterintuitive truth. Particles do not take well-defined paths. When electrons travel through an apparatus, the mathematics describing them provides no single trajectory. Instead, they explore all possible routes simultaneously, only committing to a specific arrival point when measured. Feynman's path integral formulation captures this surreal behavior elegantly. A helpful image emerges from this idea. Imagine snow falling at night. Each flake drifts uniquely, swirling through countless tiny currents of air. From afar, you perceive a soft, unified descent, yet each flake's journey is an intricate dance of possibilities. Quantum paths are even wilder, an infinity of routes woven into a single outcome. Reflecting on this reveals a quiet truth about life. When you look back on your past, events may seem to form a tidy narrative, but in the moment, each choice carried countless possible futures. Retrospective clarity can disguise the quantum-like branching underlying human experience. Another discovery disrupted classical thinking. Virtual particles flicker in and out of existence, even in perfect vacuum. Empty space isn't empty. It seethes with activity. Transient fluctuations arising from the uncertainty principle. These fleeting particles affect real phenomena, such as the Casimir effect, which demonstrates measurable forces arising from vacuum behavior alone. This can be visualized as embers glowing faintly beneath the ashes of a dying fire. The surface appears still, but look closer and you'll notice tiny sparks pulsing, appearing and vanishing in subtle bursts. What seems quiet is alive with hidden motion. The vacuum of space carries that same hidden pulse. The philosophical implication is humbling. Stillness, in both physics and life, may be an illusion. Beneath moments that feel calm, unseen forces may be shifting, preparing new possibilities. Quiet moments can hold the seeds of profound change. When quantum mechanics and special relativity merged into quantum field theory, the picture sharpened even further. The universe is not built from particles as objects, but from fields vibrating at specific energies. A particle is a ripple in a field, a localized excitation. The continuity you perceive is the smooth interaction of these ripples across space and time. To sense this gently, think of wind brushing across tall grass. From afar, the meadow seems to sway as a single surface, but stand among the blades, and you see countless individual stalks moving in their own patterns. The field is both one thing and many things, unified and fractured at once. Such is the nature of quantum fields. Philosophically, this idea hints that identity is layered. You are an individual, yet also part of larger systems, communities, species, biospheres. Boundaries soften when viewed from different scales. The quantum world suggests that separation is a perspective, not an absolute. As research progressed, even space and time appeared less continuous than once believed. At scales near the Planck length, theories predict that space-time itself becomes granular, losing its smooth geometry. Quantum gravity proposes a foamy structure, ever-shifting and ever-fluctuating, bubbling with microscopic distortions. This realm eludes current experiments, but its mathematical hints are compelling. Imagine frost forming on a window pane. Up close, the crystalline patterns are jagged, intricate, full of tiny fractures and branches. But step back, and it becomes a single sheet of shimmering ice. Space-time may behave the same way, smooth from far away, jagged underneath. Reflecting on this dissolves another layer of certainty. The foundation of reality might not be a flawless continuum, but a restless tapestry of quantum threads. The universe could be woven, not sculpted, stitched together through fluctuations too small for human senses. Even the concept of causality softens at quantum scales. Events separated by tiny distances and times can influence one another in ways that defy classical sequencing. Quantum correlations blur the line between before and after. Though macroscopic causality remains intact, the microscopic realm pulses with subtler rhythms. A metaphor helps hold this gently. Picture a choir singing in a vast cathedral. Individual voices rise and fall, overlapping in ways that make it impossible to tell which sound began first. The harmonics merge into a single, resonant whole. Quantum events exhibit a similar mingling, distinct yet inseparable in their influence. This perspective opens a philosophical doorway. Perhaps cause and effect, as you understand them, are conveniences shaped for survival. The universe itself may operate with a more intricate logic, where connection surpasses sequence, and relationships matter more than order. All these quantum discoveries, quantized energy, uncertain paths, virtual particles, vibrating fields, strip away the illusion of continuity. They reveal a universe far more textured, layered, and dynamic than classical intuition suggests. And as you descend further, the boundary between the describable and the ineffable begins to blur. Certainty is a comforting illusion, one that the human mind clings to naturally. At familiar scales, events follow predictable patterns, and causes lead reliably to effects. You drop a stone and it falls. You light a match and it burns. These expectations form a mental framework that helps you navigate the world. Yet beneath this layer of confidence lies a reality that doesn't obey the same rules. At extremely small scales, predictability dissolves, replaced by probabilities that shimmer like heat rising off distant pavement. The early pioneers of quantum physics discovered that measuring a particle's position precisely makes its momentum inherently uncertain. This is not a technological limitation or an engineering flaw. It's a fundamental feature of nature described by Heisenberg's uncertainty principle. The universe simply does not permit perfect knowledge of both properties at once. Attempts to sharpen one blur the other. This rule governs electrons in atoms, photons in beams of light, and every tiny constituent of matter. A way to visualize this involves imagining waves rolling gently across a tranquil bay. If you mark a single point on the water, you can watch its height rise and fall. But if you try to mark the wave's exact crest at every moment, the motion becomes ambiguous. The sharper your desire to pinpoint the crest, the more the water seems to ripple unpredictably. Quantum systems carry that same tension between clarity and motion. This idea carries philosophical weight. People often seek certainty in decisions, relationships, or plans, yet the quantum world shows that ambiguity is not a flaw, it's a natural state. Certainty may comfort the mind, but uncertainty allows room for change, creativity, and growth. Perhaps the universe's smallest pieces are reminding you that not knowing everything can be a quiet form of freedom. Another disruption to classical intuition emerged with wave function collapse. Before a measurement, quantum systems exist in superpositions of multiple states. An electron can occupy several positions at once, described mathematically as overlapping possibilities. But when observed, the wave function collapses into a single outcome. It's not that the electron was hiding a truth, rather, it existed as a cloud of potential until the act of measurement forced a definitive result. Consider a lantern illuminating dust in a dark attic. The beam reveals countless motes swirling in unpredictable patterns, yet if you pause the scene in a photograph, the motion freezes, collapsing onto a single, sharp frame. Quantum measurement feels similar. a fluid blur of possibilities crystallized into one moment of clarity. The underlying motion remains more complex than the snapshot suggests. Reflecting on this reveals parallels with human experience. You carry many potential futures inside you, paths you might take, choices you might make, versions of yourself you could become. Only when you commit to an action does one possibility solidify. The others remain as silent echoes, unrealized but meaningful. Quantum mechanics mirrors this branching quality of life. Another puzzle appeared when electrons and photons passed through a double-slit apparatus. If unobserved, they behave like waves, producing interference patterns on the detector screen. But when detectors monitor which slit they travel through, the pattern disappears and they act like particles. Observing the path eliminates the interference. The system changes simply because it is watched. This remains one of the most mind-bending discoveries in all of physics. A gentle way to sense this is to picture someone playing a violin in a quiet field. Far away, the sound spreads smoothly, blending into the wind. But step closer, and you hear distinct notes, bow strokes and vibrations. The act of approaching changes the texture of the experience. Quantum systems respond similarly. The presence of a measurement shifts the outcome. Philosophically, this poses a profound question: how much of reality is shaped by interaction? If observing a particle changes its nature, perhaps human attention has a subtler influence on the world as well. Focus can transform a chaotic moment into something coherent, just as neglect can let structure drift into noise. Awareness becomes a quiet sculptor. Quantum tunneling added yet another twist. Particles can pass through barriers they lack the energy to cross classically. The mathematics describing their wave functions allows a small probability of appearing on the other side, even when logic suggests they should bounce back. This phenomenon is essential to nuclear fusion in stars and underlies the function of modern electronics. An image that captures this gently is a thin veil of mist draped across a forest trail. You expect it to block your view, yet light glides through effortlessly, revealing outlines on the other side. The barrier wasn't entirely solid. It allowed certain things to slip through. Quantum tunneling operates with the same quiet defiance of expectation. This unusual behavior raises philosophical musings about obstacles in life. What appears impenetrable may contain unseen pathways. Sometimes progress emerges not from overpowering a barrier, but from flowing through tiny gaps, finding openings where none seem visible. The quantum world echoes this quiet truth. Entanglement then broke the final remaining classical boundary. When particles interact, their properties become correlated so profoundly that measuring one instantaneously influences the state of the other, regardless of distance. Einstein famously called it spooky action at a distance, troubled by the notion that information could leap across space without traveling through it. Yet countless experiments confirmed entanglement is real and essential. You can imagine this as two fireflies drifting apart in a moonlit field. Though separated by distance, they pulse with synchronized rhythms, as if their glow is connected by an invisible thread. Their unity defies the space between them. Quantum entanglement behaves with similarly poetic strangeness. This phenomenon encourages reflection about connection. Human relationships often hold unseen bonds that persist across time and distance. Memories, meanings, quiet loyalties. Entanglement suggests that connection is more fundamental than separation. Perhaps the universe itself leans toward unity, weaving threads between distant places. Quantum decoherence emerged as the mechanism that restores classical behavior at large scales. As particles interact with their environment, their delicate superpositions dissolve, replaced by definite outcomes. Decoherence explains why the macroscopic world feels stable and predictable. Your everyday reality arises not because quantum rules fail, but because they are overwhelmed by environmental complexity. This is reminiscent of ink blooming in clear water. A single drop spreads outward, losing its sharpness as it blends with the fluid around it. The original structure remains present, but becomes impossible to isolate. Decoherence performs that same dissolving act on quantum information. Reflecting on this hints at the role environment plays in shaping identity. Just as particles lose superposition through interaction, people are molded by context, culture, relationships, experiences. Stability emerges not from isolation, but from entanglement with the world. Another profound realization came from the discovery that particles have wave-like behavior. The de Broglie hypothesis proposed that all matter possesses wavelength, inversely related to momentum. Tiny objects exhibit noticeable wave characteristics. Larger objects do too, but their wavelengths are so short they appear particle-like. This duality shaped modern physics. A simple picture is a pebble dropped into a still pond. Ripples expand outward in a harmonious pattern. Imagine each ripple carrying the memory of the pebble's motion. That's how wave-like matter feels. The quantum world vibrates with patterns that encode movement, energy, and presence. Philosophically, this duality reminds you that identity is multifaceted. You can be logical and intuitive, structured and fluid, grounded and imaginative. The quantum world suggests that contradiction is not an error, it's a natural state. Quantum mechanics revealed another unsettling truth. The vacuum has a baseline energy called zero-point energy. Even at absolute zero, particles cannot be perfectly still. The uncertainty principle demands perpetual motion at microscopic levels. This energy affects phenomena like the Lamb shift and the stability of atoms. Imagine a pond at dawn. The surface seems still, yet a closer look shows subtle ripples from the faintest breeze. Even in moments of quiet, motion persists. Zero-point energy embodies that hidden restlessness. Reflecting on this reveals a quiet lesson. Beneath stillness, life continues to move. Periods of apparent calm may hold deep internal activity, processing, transformation, healing. Zero-point energy offers a metaphor for resilience. Measurements in quantum experiments always yield discrete outcomes, even though wave functions are continuous. This behavior underscores a deep truth. Nature quantizes experience at the moment of interaction. A smooth mathematical object collapses into specific values when touched by measurement. It brings to mind the moment a soap bubble bursts. The delicate sphere reflects countless colors, but its end arrives in a single, definitive pop. Quantum measurement behaves with similar precision, a continuous form reduced to a single event. This mirrors a human pattern, endless thoughts and feelings swirling until one decision crystallizes. The collapse of possibility into action becomes a defining moment. All these ideas reveal a world where certainty dissolves the closer you look. Predictability gives way to probabilities, solidity gives way to fields, and continuity fractures into quantized steps. At these scales, reality behaves like a shimmering mirage, structured yet elusive, inviting yet unknowable. And each discovery pushes you deeper into the mystery of why the universe seems to unravel beneath magnification. Space might look empty and peaceful, but that appearance is a comforting illusion created by scale. At human proportions, silence feels stable and unchanging. Yet when you shrink your perspective, the backdrop of existence becomes busy, restless, and full of hidden motion. The universe at microscopic lengths is more like a simmering sea than a calm, open void. Nothing stays perfectly still, not even when cooled near absolute zero. At small scales, rest is a concept that nature simply does not honor. physicists learned that the vacuum is not emptiness, but a field seething with fluctuations. These fluctuations are demanded by the uncertainty principle, which forbids perfect stillness. Virtual particles appear and vanish in fleeting moments, borrowing energy from the void before returning it so quickly that the universe allows the transaction. Though these particles cannot be directly captured, their effects subtly shape physical phenomena, such as the Casimir force between two uncharged plates or the fine structure of atomic energy levels. Thinking of this field is easier when you imagine a fog curling through a moonlit forest. At first glance, it seems thin and motionless, but look longer and you'll notice swirls, shifting layers, and momentary thickening as faint breezes move through unseen paths. The vacuum behaves similarly, quiet from a distance, endlessly dynamic when examined more closely. No point in this quantum fog is ever completely calm. Insights like these inspire philosophical reflections about life's constant background motion. Even when your days seem repetitive or uneventful, internal landscapes are evolving. Thoughts drift, emotions shift, and memories settle or rise again. The underlying activity may be subtle, but it is always present. Stillness rarely means stagnation. Often it means unseen transformation, mirroring the vacuum's restless energy. Another strange phenomenon emerges from the quantization of energy in bound systems. Electrons orbiting atomic nuclei cannot occupy just any distance or momentum. They are restricted to discrete energy levels. Transitions occur only when absorbing or releasing photons of specific frequencies. This quantization ensures that atoms remain stable, resisting collapse into the nucleus. Without this discreteness, matter would not behave in the reliable and structured way that allows stars, planets, and life to form. A gentle metaphor for this comes from a set of wind chimes hanging by a quiet porch. Only certain notes will ring, depending on the length and tension of the metal tubes. Strike them anywhere, and they sing their fixed tones rather than sliding continuously across a spectrum. Electrons follow similar rules, responding only with their predetermined notes, defined by quantum mechanics. This idea invites introspection about human boundaries. Just as electrons cannot take on arbitrary energies, people cannot embody every possible version of themselves at once. Growth requires stepping into new configurations, one transition at a time. Each change emits its own inner photon, carrying meaning and memory into the next stage. Another revelation from the small-scale world concerns the non-local nature of wave functions. The behavior of a particle is not constrained to a precise location until measurement. Instead, its properties stretch across regions like a probability cloud. These clouds can overlap, interfere, and evolve smoothly, governed by Schrödinger's equation. A particle's location is more a story of likelihoods than a truth carved into stone. To picture this gently, imagine dye diffusing through a clear glass of water. At first, the droplets retain their shape, but soon the color spreads in delicate gradients, impossible to outline sharply. The boundaries blur, yet the whole pattern remains connected. A particle's wave function shares this blurred elegance, dispersed, unified, and alive with subtle transitions. Philosophically, this blurring of identity suggests that rigid self-definitions may be illusions. You are not confined to a single trait or history. Instead, your identity flows outward in overlapping possibilities. Over time, certain paths sharpen through choices, while others fade. The quantum view becomes a reminder that life contains more fluidity than certainty. Interactions between wave functions introduce interference, another cornerstone of quantum behavior. When multiple probability waves overlap, they amplify or cancel each other, producing patterns that defy classical expectation. In some places, possibilities strengthen. In others, they vanish completely. The outcome depends on relationships, not just individual components. A soft way to sense this is by imagining ripples on a still pond created by two small pebbles dropped into the water. Their waves intersect, forming patterns more intricate than either ripple could produce alone. The pond's surface encodes both the individual ripples and their interactions. Quantum systems exhibit this same kind of complexity, where relationships reshape outcomes. Reflecting on interference encourages thoughts about the impact of interactions. People influence each other in subtle, far-reaching ways. Conversations, gestures, shared experiences, each becomes a wave that interacts with others, creating interference patterns across memories and emotions. The world is shaped by these interwoven ripples. Energy quantization reveals another curious effect: forbidden transitions. Some changes appear possible mathematically, but are prohibited by conservation laws or symmetry principles. These forbidden transitions shape the chemistry and behaviors of atoms and molecules, creating the intricate textures of matter. Without these rules, stars would shine differently, and biological molecules might never achieve their ornate shapes. An evocative image for this is a vaulted library where certain doors are ornamental rather than functional. They appear identical to usable doors, but when you push them, they do not open. The architecture directs your path subtly, guiding movement without explicit instruction. Quantum rules impose similar boundaries on the transformations particles can undergo. This idea stirs reflection on hidden constraints in life. Not every path is meant to be taken, even if it seems appealing. Some routes remain closed because they would lead away from your nature or values. Boundaries can serve as quiet protectors, steering you toward healthier directions. Another behavior of small-scale systems lies in wave-particle duality. Light, once thought to be purely a wave, also behaves like a stream of particles called photons. Meanwhile, matter exhibits wave-like properties. This dual nature refuses to collapse into a single category, resisting human attempts at classification. It reminds us that nature is not obligated to match our mental models. Visualizing this duality can be as simple as watching a campfire at night. Flames dance like waves, blending seamlessly, yet they are made of countless glowing sparks rising into the dark. Wave and particle intertwine naturally in the fire's motion. Quantum objects carry that same ambivalence, capable of behaving as either, depending on how they are observed. Philosophically, this duality encourages flexibility in self-perception. You can hold multiple truths at once, structured yet free, grounded yet imaginative. Identity becomes richer when seen not as a fixed point, but as a spectrum of complementary qualities. Quantum fields add another layer to this complexity. Instead of point-like particles traveling through space, physics describes matter and forces as excitations of underlying fields. Every particle is a vibration in a field that permeates the universe. This picture replaces the classical idea of objects with the more fluid notion of patterns in a larger fabric. An inviting metaphor for this is a sheet of silk stretched across a table. When touched, the silk trembles in intricate patterns, but the cloth itself remains the underlying structure. The vibrations are temporary, yet the fabric endures. Quantum fields behave similarly, the deeper substrate from which all particles arise. These concepts open the door to gentle realizations about unity. Just as fields connect every particle, underlying patterns connect every person. You are constantly shaped by shared environments, histories, and influences, each interaction adding another thread to the fabric of your identity. Zero-point motion reappears here, highlighting that even the lowest energy state contains fluctuations. A particle in its ground state still has kinetic energy because uncertainty demands motion. This property supports the stability of atoms and the persistence of molecular structures. Without zero-point motion, matter would collapse into unnatural configurations. A way to picture this is to imagine a sleeping cat whose fur rises and falls ever so slightly with each breath. Though it appears perfectly still, delicate movements continue quietly. Ground state motion in particles resembles those subtle breaths, not visible, yet essential. Such behavior encourages reflection on the quiet energy within yourself. Even during rest, your mind and body continue healing, processing, repairing. Stillness does not imply numbness. It suggests a different mode of activity. Quantum statistics provide one more twist. Particles fall into categories, bosons and fermions, governed by distinct rules. Fermions cannot occupy the same quantum state, giving matter its solidity. Bosons can crowd into shared states, enabling lasers and superfluidity. These statistical behaviors shape the architecture of the physical world. A soft metaphor for this is a flock of birds gliding across the sky. Some maintain careful spacing, respecting invisible boundaries, while others cluster tightly in shimmering formations. Their differing patterns echo the contrasting behaviors of fermions and bosons. This variety invites contemplation about diversity in human expression. People embody different rhythms, preferences, and emotional textures. The world becomes richer when these differences coexist, creating harmony through contrast. At these tiny scales, space itself stops behaving like a stage and becomes an active participant. Distances flicker with uncertainty, fields ripple unpredictably, and particles wander through blurred identities. Predictability fades the deeper you look. Yet within this strangeness lies a coherent, interconnected tapestry, one that holds the blueprint for every star, planet, and life form. The chaos of small scales becomes the foundation for the order of the cosmos. Measurements seem simple at everyday scales, yet in the quantum world, the act of observing becomes a transformative event. At large sizes, you can look at a mountain or a tree without altering them. But as you descend into the microscopic landscape, the observer and the observed begin to intertwine. Reality at small scales is delicate enough that the slightest interaction can redirect its path. What appears stable becomes responsive, sensitive, and surprisingly participatory. Physicists learned this through experiments revealing that particles do not possess definite attributes independent of measurement. Instead, their properties emerge from interactions with measuring devices or environments. A particle's momentum, position, or spin does not exist as a crisp fact until something disturbs it. Before that interaction, the particle resides in a haze of probabilities described by a wave function. Measurement collapses this haze into a single outcome, shaping the answer you receive. A poetic way to imagine this is to picture a book whose pages continually shuffle until you reach out and touch it. When your fingers press against the cover, the pages settle into a particular order, revealing one story instead of all possible stories. Quantum measurements behave similarly. The act of reaching into the system selects a single narrative from countless potential ones. Reflections on this phenomenon invite questions about human perception. Every interaction, conversation, or choice on your part alters some trajectory in your life or in someone else's. Even your silent presence in a room influences the atmosphere. Just as measurements change particles, your awareness and decisions subtly shape the world around you. Wave function collapse becomes even stranger when considered in double-slit experiments. When particles pass through two slits without being observed, they create interference patterns, a signature of wave-like behavior. But when detectors watch the slits, the pattern vanishes, replaced by classical behavior. The mere possibility of acquiring which path information changes the outcome. Knowledge and potential knowledge affect reality differently. To capture this visually, imagine a quiet stage where dancers move freely when no spotlight is present. Their steps overlap in fluid, ghost-like patterns. Once a spotlight shines, the movements snap into sharply defined forms. The softness of uncertainty vanishes under attention. Quantum systems react the same way to spotlights of measurement. This invites introspection about how attention influences your experience of life. When you focus intensely on one aspect of your day, its textures sharpen, sometimes at the cost of noticing gentler, broader patterns. Conversely, allowing your awareness to soften can reveal connections you might otherwise overlook. Attention becomes a form of measurement that shapes your internal landscape. Another hallmark of small scales is decoherence, the process by which quantum superpositions vanish when systems interact with their environment. Superpositions allow particles to exist in multiple states at once, but they are fragile. The faintest touch from surrounding particles or radiation destroys them, forcing the system into a definite state. Decoherence bridges the quantum and classical worlds, explaining why you do not see superpositions in everyday life. A metaphor for decoherence can be found in a serene lake at dawn. At first, the water reflects the sky perfectly, merging two realities into one. But as birds land, insects move, or a breeze stirs the surface, the reflection shatters into countless fragments. The merge of possibilities dissolves into a single ordinary scene. Quantum superpositions share this fragility when disturbed by their environment. Decoherence encourages reflection on vulnerability in human experience. Moments of clarity or inspiration often feel delicate, easily disrupted by noise, stress, or distraction. Holding on to these states requires patience, quiet, and intentional protection, much like shielding a quantum system from interference. The role of the observer becomes even more intriguing in delayed choice experiments. These experiments show that decisions made after a particle travels through a setup can still affect its earlier behavior. It seems to suggest that future choices influence past events on microscopic scales. Though not time travel in any classical sense, this reveals that quantum systems do not follow the tidy temporal order we expect. A gentle image to support this idea is a storyteller who revises a tale's ending after it has already begun. When the ending shifts, earlier chapters take on new meaning, as if they were always leading toward that new conclusion. The story and its interpretation appear to evolve together. Quantum experiments echo this strange coupling of before and after. Philosophically, this inspires thoughts about reinterpretation in your own life. Decisions you make today can change the meaning of earlier experiences. A difficult memory might gain new value after later growth. Past and present are not as cleanly separated as they seem. Meaning flows both ways. Entanglement deepens this mystery. When two particles become entangled, their properties link so tightly that measuring one instantly determines the state of the other, no matter how far apart they drift. Einstein called this spooky action at a distance, though it does not transmit information faster than light. Instead, entanglement reveals that quantum systems are not isolated islands, but strands in a shared tapestry. To imagine this softly, think of two lanterns connected by an invisible thread. Light one lantern, and the other glows in harmony, even across great distance. They respond together, though neither sends a message to the other. Their connection is built into their shared origin. This opens a philosophical doorway toward ideas of connection in human relationships. Emotional bonds often transcend distance. A message from someone you care about can lift your mood instantly. Memories of shared experiences can comfort you even when the other person is far away. Entanglement becomes a poetic reminder of these invisible threads. Measurement also reveals limits on the precision with which certain pairs of properties can coexist. The Heisenberg uncertainty principle states that some quantities, like position and momentum, cannot both be known with perfect accuracy. The more precisely you try to measure one, the more the other becomes uncertain. This is not a flaw of instruments, but a fundamental feature of nature. A peaceful metaphor for this involves gazing at a candle flame in a darkened room. You can focus intently on the flame's detailed shape, or you can let your eyes relax and sense its warm glow across the room. But you cannot hold both the sharpness and the ambience at once. The deeper you commit to one, the more the other slips away quietly. This naturally leads to reflection on balance. Some aspects of life cannot be mastered simultaneously. Concentration on one goal may blur another area. The uncertainty principle becomes a quiet guide, suggesting acceptance rather than resistance when confronted with competing priorities. Measurement also shapes time in the quantum domain. Certain transitions or decays occur only when systems interact with their surroundings. In some circumstances, frequent observation can even slow a particle's evolution, a phenomenon called the quantum Zeno effect. By checking too often, you can prevent change. To picture this gently, imagine a pot of water on the stove. When left undisturbed, it warms steadily and eventually boils. But if you continuously lift the lid to inspect it, the heat escapes, delaying the boil. Quantum systems behave similarly when subjected to relentless inspection. This idea sparks introspection about over-monitoring yourself. Constant scrutiny can stall progress, while allowing space and patience can foster natural growth. Sometimes the most transformative changes occur when you stop checking constantly. Small-scale measurement introduces another twist called contextuality. The outcome of a quantum measurement can depend on which other measurements are being performed alongside it. Properties are not absolute, but depend on the broader experimental context. Nature reveals different facets depending on how you ask your questions. A metaphor for contextuality emerges in observing clouds. Depending on the angle of sunlight or the position of the observer, the same cloud may look bright white, soft gray, or tinged with gold. The cloud has no single true color. Its appearance depends on conditions surrounding it. Quantum properties share this situational quality. This perspective nudges you toward flexibility in understanding others. People show different sides depending on context, environment, mood, or company. No single moment captures the whole person. At microscopic scales, measurement is inseparable from the fabric of reality. The act of observing changes the observed. The environment shapes possibilities. Time and meaning shift together. Entanglement binds distant entities into unified systems. Context becomes part of truth. Though these behaviors defy classical intuition, they anchor the structure of everything large enough to seem stable. What looks chaotic or fragile at tiny scales ultimately supports the cosmic order you see around you. At everyday scales, space feels perfectly smooth, like an infinite canvas stretching in every direction. You can walk across a room, trace a curve with your hand, or imagine the vast distances between stars without sensing any gaps beneath your feet. But as the journey descends toward the smallest conceivable lengths, that smoothness begins to unravel. The continuity you take for granted starts to flicker, revealing hints of something granular and unfamiliar. Quantum field theory suggests that even empty space teems with activity. At unimaginably tiny scales, virtual particles burst into existence and vanish again in fleeting pairs. These fluctuations create a restless ocean beneath the calm surface of space-time. What appears silent and still on macroscopic levels becomes turbulent and foamy when examined with extreme precision. Space is not a quiet void, but a field of incessant motion. A soft way to imagine this is to picture the deep sea on a perfectly calm day. From far above, the surface looks smooth and unbroken. But plunge below and you find swirling currents, drifting particles, and tiny eddies in constant motion. Similarly, the more closely you dive into space-time, the more chaotic its interior becomes, revealing layers of movement that ordinary perception cannot grasp. This imagery encourages you to think about how much exists beyond immediate awareness. Beneath your everyday routines lie emotions, habits, memories, and instincts that swirl beneath the surface. They may seem quiet until you pause long enough to notice the subtle undercurrents shaping your choices. The inner world, like space-time, contains hidden textures. Approaching the Planck length, the smallest meaningful scale in physics, leads to profound conceptual challenges. According to current theories, attempting to probe distances this tiny would require energy so extreme that gravity itself becomes overwhelming. Rather than revealing more detail, any deeper investigation collapses into uncertainty. The very act of pushing further breaks the framework used to describe the world. A poetic image for this involves observing fog illuminated by a lantern at night. You can see shapes forming and dissolving, but the closer you try to look, the more the light scatters, erasing clarity. The fog resists precise examination, refusing to sharpen into a detailed picture. Reality near the Planck scale behaves with similar reluctance, dissolving into ambiguity instead of offering sharper focus. This leads to a philosophical consideration. Some aspects of existence do not become clearer with scrutiny. Certain questions in life resist precise answers, no matter how long you sit with them. The more intensely you search for definition, the more the edges blur. Acceptance becomes an act of wisdom rather than defeat. Gravity and quantum mechanics collide most violently at these tiny scales. General relativity describes gravity as the curvature of space-time, while quantum theory portrays forces as exchanges of discrete particles. When combined under extreme conditions, these perspectives clash, generating mathematical contradictions. Something new, perhaps a quantum theory of gravity, is needed to reconcile them. A metaphor for this tension can be found in trying to overlay two maps of the same landscape, one drawn as a watercolor painting and the other as a technical blueprint. Both convey truth, yet they follow different rules. To overlay them too precisely, and the mismatched lines and shapes create confusion. Gravity and quantum physics coexist, but the deeper you zoom, the more their differences conflict. This blend of incompatible perspectives invites reflection on human experience. You may hold multiple truths about yourself, rational goals, emotional needs, memories, and ambitions that do not always align seamlessly. Rather than forcing perfect consistency, allowing each truth to coexist can bring balance. As space-time becomes grainy, classical geometry loses meaning. Concepts like location, direction, and distance begin to behave strangely. Instead of smooth curves and lines, theories propose fluctuating patches, jittering nodes, or networks of discrete connections. Space may not be continuous. It might be woven from microscopic units that flicker in and out of configuration. To visualize this softly, imagine a tapestry viewed from a great distance. The image appears smooth and continuous. But when your eyes move closer, individual threads stand out, each twist and knot a tiny component contributing to the whole. Space-time too might be composed of countless invisible threads stitched together into the illusion of continuity. This idea encourages contemplation about how many people and moments have woven into the tapestry of your life. Each tiny influence, a glance, a comment, a quiet moment, becomes a thread contributing to your story. Meaning often emerges from pieces too small to notice individually. Time itself becomes uncertain near the Planck scale. Instead of unfolding in a steady linear sequence, time might fragment, loop, or ripple. Some theories suggest that intervals shorter than the Planck time lose definition entirely. Events may not occur in a neatly ordered sequence. Instead, reality may allow subtle blurring between what comes before and after. A metaphor can be found in listening to distant thunder during a storm. The rumbling sound arrives in layered echoes, overlapping and merging. You cannot easily pinpoint which vibration came first. The boundaries between moments dissolve. Quantum time may share this fluid, echoing quality. Thinking about time in this way opens the door to gentle introspection. Experiences in your memory sometimes overlap, bleed together, or rearrange themselves depending on mood or perspective. The past is not always fixed. It reshapes itself as you grow. Strange as it seems, some models propose that space-time itself might not be fundamental. Instead, space and time could emerge from deeper structures, networks of information, entanglement patterns, or energy relationships. In this view, the universe is not built from particles embedded in space. Rather, space emerges from how those particles interact. An image to accompany this concept involves watching frost form on a window pane. The cold glass begins to sprout branching crystals that gradually weave into a delicate pattern. The frost looks like a structure that has always been there, yet it materializes from invisible conditions. Space may arise in a comparable way, a structure emerging from deeper rules. Such ideas inspire reflection on how meaning arises in your own life. You may feel that certain aspects of your identity have always existed, yet many emerged from relationships, experiences, or challenges. What feels fundamental may be born from deeper processes. Probing space-time at microscopic scales also introduces quantum foam, a concept suggesting that space churns with tiny fluctuations of geometry itself. Distances expand and contract, energy spikes appear unpredictably, and tiny bubbles of curved space-time form and vanish. The geometry of reality becomes frothy and restless. To soften this idea, imagine looking at soap bubbles clustering in a sink full of warm water. The bubbles wobble, merge, burst, and reform in new shapes. At small enough scales, space-time may behave with this same unpredictable dance, full of ephemeral structures that appear briefly and vanish without a trace. This picture invites you to accept the fluidity in your own life, times when plans shift suddenly, when new paths appear unexpectedly, or when uncertainties invite growth. Stability is precious but not absolute. Finally, the breakdown of space-time smoothness teaches a humbling lesson. The universe is not constructed for human comfort. The world shrinks into unfamiliarity as scales descend, revealing that existence has layers far removed from intuition. Yet these bewildering structures underpin everything familiar: stars, oceans, breath, warmth, memory. At certain depths of reality, the universe feels as if it begins to question its own rules. Concepts that once behaved reliably, position, momentum, identity, grow slippery and contradictory. Instead of offering clarity, nature answers with probability clouds and shifting boundaries. It becomes increasingly clear that certainty is something humans invented, not something the cosmos consistently provides. Quantum superposition is one of the first ideas that challenges familiar logic. A particle can occupy multiple states at once until measured. In the mathematical language of quantum mechanics, this isn't metaphor. It's a literal description of how tiny systems evolve. Reality does not commit to a single version of itself, until interaction forces a choice. A calming way to sense this is to picture a lantern glowing behind a thin curtain. From the outside, you can see soft, overlapping shapes of light, none fully distinct. Only when the curtain is pulled aside does the light sharpen into a single, indefinite outline. Superposition behaves in a similar manner, letting possibilities overlap gently until the universe draws the curtain. This idea often raises a quietly existential thought. How many versions of your future exist in your imagination at once, layered like soft lights behind a curtain? Only actions, the measurement of life, collapse them into something real. Quantum entanglement adds a deeper twist. Two particles can become linked so intimately that the state of one instantly determines the state of the other, no matter the distance between them. Einstein found this unsettling, calling it spooky action at a distance. Yet countless experiments, from Bell's theorem tests to modern quantum computing prototypes, confirm this strange connection. A poetic reflection of entanglement appears in the way distant storms can share the same wind pattern, or how two separate instruments can fall into harmony without touching. There is a quiet beauty in connection that transcends distance, whether between particles or people. This inspires a soft moment of reflection. Some relationships in life feel like this. Two souls influencing one another, even when separated by miles or silence. The connection remains, invisible yet unmistakable. Wave-particle duality pushes the contradictions further. Light behaves like a wave when spreading across space, yet acts like a particle when interacting with matter. Electrons show the same dual nature. It isn't indecision. Nature truly allows both descriptions depending on context. The double-slit experiment famously demonstrates this dual identity, revealing interference patterns even when particles traverse the experiment one at a time. To sense this gently, imagine a musician playing a note in a large hall. The sound waves fill the room, curling around pillars, weaving through air. Yet the musician also plucks a single string, a discrete event, producing that vast wave. Quantum systems move between these identities in a similar dance, oscillating between the localized and the expansive. This duality invites a philosophical thought. Sometimes you feel solid and defined, a single string, clear in your direction. Other times you feel fluid, diffused, spread across many roles and emotions. Both are valid expressions of being human. Uncertainty lies at the heart of quantum behavior. Heisenberg's uncertainty principle states that certain pairs of properties, like position and momentum, cannot both be known with perfect precision. The more you know of one, the less you can know of the other. This is not a measurement flaw. It's a fundamental feature of nature. A metaphor emerges in watching fireflies drifting over a field. You see flashes of their light, but their paths remain elusive. The closer you try to track a single one, the more its movement defies prediction. Reality at small scales flickers with this same evasive charm. Reflecting on uncertainty can feel strangely comforting. Life rarely hands out complete clarity. Paths shift, circumstances change, and expectations bend. Uncertainty isn't a flaw in the world, it's a natural ingredient in growth, as intrinsic as breath or motion. Another astonishing concept is quantum tunneling. A particle can pass through a barrier it should not have enough energy to cross. This phenomenon enables nuclear fusion inside stars and underpins the operation of technologies like flash memory and scanning tunneling microscopes. Nature, at its smallest levels, refuses to obey classical boundaries. The image of tunneling pairs well with the idea of morning light seeping through gaps in curtains. Even when the room is sealed in darkness, thin threads of light find a way inside. Quantum particles navigate obstacles with a similar grace, slipping through barriers that appear impenetrable. This invites a moment of introspection. The obstacles in your own path may not be as absolute as they seem. Solutions sometimes arrive unexpectedly, slipping through cracks you never realized existed. Quantum decoherence marks the transition between quantum strangeness and classical stability. When particles interact with their environment, superpositions collapse, and the fuzzy quantum haze sharpens into the definite forms you recognize. Decoherence is why humans don't experience macroscopic superposition. Everyday objects constantly interact with countless environmental factors, erasing quantum ambiguity. To visualize decoherence, think of a delicate ink droplet dispersing through water. At first, the drop holds its shape, a clear, defined boundary. As it mixes with its surroundings, the lines blur until the original form dissolves into the larger fluid. Quantum systems experience a similar dissolution of identity when exposed to the environment. This leads to a gentle philosophical realization. Staying completely defined is hard when surrounded by countless external influences. You change, adapt, blend with environments, and reorganize yourself. Change is not loss, it's transformation. Experiments probing deeper into quantum gravity suggest that space-time itself might inherit quantum properties. If the fabric of the universe is ultimately made of discrete, fluctuating units, then particles and space are two aspects of a single underlying structure. At this level, the distinction between things and the space they occupy begins to blur. A softer interpretation resembles watching fog blend seamlessly with the air. You cannot separate one from the other. They merge into a single unified atmosphere. Quantum space-time hints at a universe where boundaries between entities are equally porous. This unity prompts reflection on how interconnected your own life is with the world around you. You're not separate from your environment. You're shaped by it and contribute to it. Moving deeper into theoretical territory, certain models propose that reality may resemble a vast evolving information network. Particles, forces, and space-time could emerge from patterns of information flow, not unlike the way complex images form from simple pixels. In this view, the fabric of existence might be built from fundamental bits of quantum information. To soften this concept, imagine snowflakes falling onto a quiet field. Each flake is a tiny pattern, but together they form a smooth, continuous blanket. Individual units give rise to something larger and more coherent, just as quantum information might give rise to the structure of the universe. This brings an introspective echo. Your life is composed of countless small choices, moments, and feelings, each one a tiny bit of your unfolding story. Together, they weave a reality far greater than any single moment suggests. The quantum world's contradictions, particles acting like waves, objects occupying multiple states, connections spanning impossible distances, all point toward a universe far more flexible and mysterious than intuition suggests. Instead of breaking, reality bends gracefully at small scales, adapting to rules that only become visible in silence and patience. At extremely small scales, the universe begins to resemble a place where ordinary definitions dissolve. Distance, duration, direction, the familiar anchors that help you navigate life, start slipping away as if the fabric beneath them is fraying. What remains is a trembling landscape of probabilities and shifting geometries, hinting that reality may be woven from something more primitive than space and time themselves. Modern physics suspects that smooth space-time is only an illusion of scale. Beneath the surface, quantum gravity theories propose a graininess, a lattice so tiny that even atoms appear vast in comparison. The Planck length, around 10 to 35, 10, 10, 35 meters, defines this territory. Below it, No instrument can meaningfully distinguish one point from the next. A helpful image is to imagine looking at a calm ocean from above. It appears flat and serene until you lower your eyes toward the surface. Ripples become waves, waves become peaks and troughs, and the closer you get, the more chaotic the details appear. At the smallest scales of space-time, the ocean of reality churns in a similar, unpredictable rhythm. This realization often brings a quiet melancholy. Everything you've ever experienced, roads you've walked, stars you've seen, moments you've loved, relies on a backdrop that may not be as stable as it feels. There's beauty in that fragility, but also a gentle sadness. Hints of this fracturing appear when scientists study black holes. Theories suggest that near the event horizon, quantum effects become strong enough to disrupt classical geometry. Space-time stretches, twists, and vibrates under the weight of gravity and quantum uncertainty combined. Instead of a smooth fabric, the region resembles a storm of tightly packed information. A softer metaphor emerges from watching a candle flame in a quiet room. From afar, the flame seems steady. Up close, its edges shimmer and pulse, revealing constant unseen turbulence. The quantum structure of space-time likely flickers in the same hidden way. Thinking about this flickering invites reflection about personal boundaries. Your life may look steady from a distance, yet up close it is full of small shifts, doubts, hopes, contradictions, all woven into who you are. Stability and chaos coexist more often than you might admit. String theory presents one attempt to reconcile the small-scale turmoil. Instead of point-like particles, it imagines tiny vibrating strings whose frequencies determine the properties of matter. In this model, dimensions beyond the familiar threefold in tightly curled shapes, known as Calabi-Yau manifolds. These hidden dimensions could help account for gravity's weakness and the universe's underlying symmetries. Visualizing curled dimensions can feel abstract until you think of the way a violin string holds both length and thickness. From far away, the string looks like a simple line. Up close, you see detail, texture, curvature, vibration. Additional dimensions might exist with the same subtlety, shaping the cosmos quietly. Such thoughts tend to evoke a wistful kind of wonder. The idea that reality might hide entire directions, curled too small to perceive, makes the universe feel both magnificent and distant, as if most of its truth is whispered behind a closed door. Loop quantum gravity takes a different path. Instead of strings, it describes space-time itself as a network of discrete loops. Surface areas and volumes become quantized, like pixels in a cosmic display. This view removes the need for extra dimensions, but introduces a universe built from intricate, interlocking structures. A gentle comparison arises when looking at frost spreading across glass. Up close, the crystalline branches form repeating patterns, each tiny structure contributing to a larger image. Space-time, if granular, may display a similarly delicate architecture. Moments like these can feel strangely lonely. If space-time is pixelated, finite and ever-changing, then your existence unfolds on a stage far more fragile than intuition suggests. And yet, that fragility feels honest, a reminder that all things, even universes, are built from small, transient pieces. On the frontier of quantum cosmology, certain theories propose that the universe might have emerged from a quantum fluctuation, a spontaneous jitter in a field without classical cause. If so, the notion of a beginning becomes less like a boundary and more like a transition. Before time flowed smoothly, there may have been only a foaming sea of quantum possibility. A gentle emotional echo appears when thinking about your own beginnings, how your identity, relationships, and memories emerged not from a single moment, but from countless subtle influences that slowly coalesced into the person you are now. Another idea suggests that space-time could be emergent, not fundamental. Much like temperature emerges from molecular motion or pressure from countless collisions, space-time might arise from deeper informational patterns. This perspective rearranges the hierarchy of existence. Particles and forces are no longer foundational. They are byproducts of something even more hidden. To make this feel tangible, imagine weaving a cloth. Up close, there are only threads crossing one another. The concept of fabric emerges only when enough threads form a coherent pattern. Space-time may be the same, a larger phenomenon emerging from countless microscopic interactions. Such reflections highlight an emotional truth. The meaning you experience in life often emerges from subtle threads. Connections, memories, quiet gestures. None significant alone, but profound in harmony. Research on the holographic principle adds yet another layer. It proposes that the three-dimensional universe may be a projection of two-dimensional information encoded on a distant boundary. Gravity, black holes, and quantum fields might be shadows cast by mathematical processes happening at this cosmic edge. A metaphor can be drawn from watching sunlight stream through a window. Dust particles glow briefly in the beam, and though the light seems thick and full, its origin lies far outside the room. Our universe, too, might be a glowing interior shaped by distant informational surfaces. This line of thought invokes a quiet humility. If reality is a projection, then much of what feels solid is actually part of an unimaginably large and subtle tapestry. And yet, your experiences within it remain meaningful and intimate. Quantum fluctuations, holographic boundaries, and emergent space-time together paint a picture of reality that becomes increasingly abstract. At the smallest scales, the foundations of existence blur into patterns so delicate they escape all direct observation. The universe does not break down, it simply becomes too intricate to describe with ordinary notions. A sense of peaceful melancholy follows. There is comfort in accepting that not all mysteries require solutions. Some truths are better felt than defined, like the warmth of a memory or the stillness of night. The journey into the small reveals that the universe hides its deepest secrets behind shimmer and uncertainty. And yet, you remain part of that mystery, a fleeting arrangement of particles woven into a consciousness capable of wondering about its own origins. The deeper physicists look into the fabric of existence, the more the notion of a foundation seems to slip away. Instead of encountering a final layer, the floor of reality, they find more uncertainty, more flicker, more ambiguity. It's as if the universe refuses to give a firm answer, whispering that certain truths might be forever out of reach. Attempts to describe the smallest scales often lead to equations that diverge or collapse under their own complexity. Classical intuition falters because the world beneath atoms does not behave like the world above them. Space loses its continuity. Time loses its steady rhythm. Even causality, the backbone of everyday experience, becomes blurred. A gentle sadness forms in this realization. Human minds evolve to navigate predictable environments, where stepping forward leads somewhere and events follow reasonable patterns. Facing a universe that abandons those patterns can feel like encountering an ancient, indifferent ocean, beautiful, but unmoved by your desire to understand it. The Planck scale stands at the center of this mystery, marking the point where current theories break down. Length, duration, and energy condense into quantities so extreme that no instrument can probe them directly. Beneath this threshold, geometry itself ceases to behave in familiar ways, leaving only conjecture. There's something poetic about standing at the edge of knowledge and knowing that some territories might remain unreachable. It mirrors the personal experience of confronting questions about life, purpose, and identity. the ones that never truly resolve, no matter how many times you revisit them. Quantum mechanics adds an entirely different challenge. Particles seem to carry multiple states simultaneously until observed. Their positions remain uncertain, their behaviors probabilistic. Instead of solid trajectories, nature offers smudged possibilities. This isn't a flaw in perception, but a fundamental feature of the universe. Thinking of reality as probability waves evokes images of fireflies drifting through a summer night, each path a shimmering maybe. You never know exactly where the next glow will appear, yet the pattern as a whole feels peaceful, almost meditative. Emotional parallels arise naturally. Life often unfolds in probabilities, hopes that may or may not materialize, relationships that flicker into view before drifting away. There is rarely a definite map, only a range of outcomes shaped by choices and circumstance. When researchers attempt to merge quantum theory with general relativity, contradictions appear instantly. Gravity, so graceful for planets and stars, becomes unruly in the quantum realm. Space bends, twists, and fluctuates in ways that mathematics struggles to contain. Certain calculations even predict infinite density, a sign that the theory has left its domain of validity. These infinities can feel like conceptual cliffs. Standing before them evokes a quiet awe, the same feeling that comes when looking up at night and remembering that the sky is unimaginably vast. One promising idea suggests that space-time might emerge from entanglement, the mysterious quantum link that causes distant particles to behave as a single system. If entanglement fades, space-time itself dissolves. Under this view, reality is more like a vast network of relationships than a physical backdrop. A soft analogy appears when thinking about your closest bonds. Identity often emerges from connection, shared moments, shared memories, shared emotions. Without these ties, the sense of self feels thinner, less defined. Perhaps the universe follows the same pattern. Connection precedes structure. Research into black hole information also reshapes understanding of fundamental reality. Information falling into a black hole appears lost, but quantum theory states that nothing truly vanishes. To reconcile the paradox, some models propose that information becomes encoded in subtle fluctuations of space-time's boundary. These ideas bring to mind the way your own past, choices, regrets, triumphs, sometimes feels encoded in faint emotional impressions, surfacing unexpectedly. Even events that felt forgotten continue shaping you in ways you don't always perceive. Holographic descriptions of the universe continue to gain traction, suggesting that the cosmos might have fewer degrees of freedom than it appears. Everything experienced in 3 dimensions could arise from processes happening on a distant, flat surface. Such a model defies intuition, yet the mathematics carries undeniable elegance. There's a reflective mood in contemplating a universe where depth is emergent rather than fundamental. Much like the difference between a dream and the memory of a dream, both feel vivid, yet one carries more weight. Reality's weight might come not from structure, but from perception. Cosmic inflation adds another layer of mystery. If the early universe expanded exponentially, regions once connected drifted beyond each other's horizons. Their physical states froze into quantum imprints that shape the galaxies we see today. The vast cosmos, everything, may be the fossilized echo of microscopic fluctuations. This echoes the way fleeting moments sometimes define entire chapters of a person's life. A single conversation, a single realization, or a single night can influence decades that follow. Efforts to find a theory of everything face an emotional undertone rarely discussed. Researchers confront a quiet fear that nature might not offer a single unifying explanation. Instead, multiple frameworks could coexist, each illuminating one region of reality but none capturing the whole. It mirrors the human experience of searching for meaning. People often yearn for one clear, defining purpose, only to discover that meaning shifts with perspective, age, ease, and circumstance. There may not be a final answer, and that's okay. Mathematical models increasingly suggest that smooth space-time might be a macroscopic illusion, the result of averaging countless micro-events. Much like a forest appears continuous from afar, but resolves into individual trees up close, reality might only seem steady because the true structure is hidden beneath layers of scale. Images of fog come to mind, a soft haze that looks solid until you step into it. The boundary that seemed clear dissolves, leaving only drifting particles suspended in air. Reality's deepest layers might possess the same shimmering ambiguity. The more scientists explore this ambiguity, the more it becomes clear that the universe is not obligated to fit human expectations. It behaves according to its own logic, unconcerned with simplicity or comfort. Yet this indifference carries a strange serenity. The cosmos is what it is, whether or not we grasp it fully. Contemplating the breakdown of reality at small scales leads to an emotional truth. Uncertainty isn't only a scientific principle, it's also a human condition. You navigate life through shifting circumstances, imperfect knowledge, and incomplete understanding. Still, you move forward. There's comfort in embracing the unknown. Just as quantum fields fluctuate without fear, you too can allow space for uncertainty, accepting that some questions might never resolve, but can still guide you toward curiosity and wonder. The smallest scales teach that reality's roots are subtle, restless, and intricate. Yet despite this complexity, the universe manages to produce stars, oceans, consciousness, and the quiet ability to reflect on existence itself. And in that reflection, you find a kind of companionship with the cosmos. Both you and the universe carry depth beneath the surface, complexity beneath appearance, and mysteries that will never be fully unraveled. Across decades of research, scientists have uncovered a striking pattern. Whenever old laws of physics fail, new frameworks rise to replace them. The breakdown of reality at tiny scales isn't the end of understanding. It's the beginning of a deeper layer waiting to be discovered. This cycle plays out like a quiet cosmic rhythm, repeating across history. Newton's laws once seemed absolute, describing motion with precision and elegance. They worked beautifully for apples, arrows, and planets, yet they fractured under extreme gravity and high speeds. Instead of a dead end, their failure opened the door to Einstein, who revealed space-time as flexible and alive. General relativity carried physics further than ever before, predicting black holes, gravitational waves, and the bending of light. Still, its brilliance dimmed in the subatomic world. Tiny scales resisted its authority, behaving like dancers choreographed by a completely different set of rules. Here, quantum mechanics stepped in. Quantum theory wasn't an upgrade to Einstein's vision, but a parallel universe of logic. It embraced uncertainty, randomness, and duality. Light behaved as both particle and wave. Electrons hovered in probability clouds, and empty space seethed with energy. This new paradigm explained the invisible machinery behind chemistry, stars, and technology. Even so, quantum physics falters when combined with gravity. Attempts to merge the two theories generate contradictions and infinities. It's as if the universe maintains two languages, one for the very large, another for the very small, and hides the dictionary that connects them. This tension fuels the search for a deeper description of nature. Approaches like string theory propose that reality's building blocks aren't point-like particles, but vibrating strands of energy. Different vibrations create different particles, the way plucked strings create musical notes. Space and time themselves might emerge from these fundamental vibrations. Other ideas explore loop quantum gravity, where space-time becomes granular, woven from tiny loops like threads in an invisible fabric. Instead of smooth geometry, the universe would resemble a cosmic tapestry, each loop carrying a sliver of area or volume. These propositions offer hope that the contradictions between relativity and quantum mechanics might someday reconcile. Yet, none have been confirmed, leaving scientists with a mixture of optimism and humility. The universe continues to reveal clues while guarding its deepest truths behind layers of complexity. Some of the boldest theories suggest that space-time is not fundamental, but emergent, the outcome of even deeper processes involving quantum entanglement. Under this view, distance, geometry, and even the passage of time arise from invisible networks of information. Reality becomes a kind of story, woven from interconnections rather than objects. Echoes of this appear in everyday life. Your identity feels solid, yet it emerges from relationships, memories, and experiences, a tapestry rather than a single thread. Perhaps the universe behaves the same way, forming structure only through countless interactions beneath the surface. Efforts to map the quantum vacuum reveal that emptiness is anything but empty. Virtual particles continually flare into existence and vanish in an instant. Fluctuations ripple through all of space, creating a frothy, restless background. This seething activity might hold the key to understanding why the universe has mass, structure, and stability. Thinking about such a foundation feels similar to contemplating your own inner world, the thoughts, impulses, and feelings that flicker behind every action. Much of what shapes you happens beneath conscious awareness, yet it directs your life in quiet but decisive ways. Singularities remain another source of confusion and fascination. At the heart of black holes, equations collapse, predicting infinite density in finite space. Most physicists believe this infinity isn't real, but a sign that current theories are incomplete. Whatever truly lies inside may demand an entirely new description of space and time. This mirrors moments in life when familiar frameworks break apart, a belief, a relationship, or a plan dissolving abruptly. The rupture forces a new perspective to emerge, often more nuanced and resilient than before. Experiments probing quantum behavior continue to reveal paradoxes. Particles influence each other across vast distances, defying classical limits. Observations shape outcomes, as if nature waits for a quiet acknowledgement before choosing a path. Such behaviors hint at an underlying unity across the universe, a hidden coherence beneath apparent chaos. Reflecting on this unity evokes a sense of belonging. Even within uncertainty, there's structure. Even in randomness, there's pattern. And even when answers remain elusive, the search for understanding carries beauty in its own right. As theories evolve, physicists grow increasingly comfortable with the idea that some mysteries might never fully resolve. Perhaps reality is layered, recursive, and endlessly self-referential. Perhaps there is no final theory, only a succession of deeper models, each revealing a little more than the last. Yet this uncertainty doesn't diminish the wonder of the universe. Instead, it magnifies it. The cosmos invites exploration, not because it offers completion, but because each discovery leads to another horizon. Knowledge expands the way galaxies drift apart, opening new space, new questions, new possibilities. The breakdown of reality at small scales suggests that the universe is stranger than imagination alone could conjure. But strangeness doesn't imply failure. It hints at a richness that transcends human intuition, nudging curiosity forward like a gentle tide against a shoreline. Contemplating such depth encourages a softer approach to the unknown. Instead of demanding clarity, you can allow yourself to rest in the ambiguity. The universe has been evolving for billions of years. It is patient with its mysteries. You can be patient with your own. Even if nature never reveals its ultimate foundation, the quest for understanding creates meaning. The journey shapes those who undertake it, fostering resilience, creativity, and connection. And perhaps this is the universe's quiet gift, the opportunity to seek answers, not necessarily to find them. In the end, the smallest scales of existence demonstrate that reality is not rigid. It's dynamic, playful, and sometimes contradictory, yet always capable of forming beauty. From quantum fields, stars rise. From uncertainty, life unfolds. From mystery, awareness blooms. And in this unfolding, you find a place within the cosmos, not separate from the strangeness, but part of it, shaped by the same forces, carried by the same currents, illuminated by the same quiet glow of the unknown. As we rise slowly from the smallest layers of existence, the strangeness we've explored begins to settle into something gentle and almost comforting. The quantum world, with all its unpredictability, stops feeling like a threat to understanding and instead becomes a quiet reminder that reality is richer than the narrow slice our senses can perceive. The mysteries you've drifted through tonight aren't obstacles, they're invitations. And each unanswered question is a doorway left open for you, for science, for future minds who will wander these realms long after this moment ends. Throughout this journey, we watched the rules of everyday experience soften and dissolve the deeper we traveled. What seemed solid became probabilistic. What felt certain became fluid. What appeared simple revealed hidden intricacies dancing beneath the surface. Yet rather than leaving you unmoored, these shifts reveal a truth the universe has whispered since its earliest moments. Complexity does not replace beauty. It enhances it. Even chaos has structure. Even uncertainty has rhythm. Even the unknown can be a place of rest. The farther scientists push into the quantum frontier, the clearer it becomes that the universe is layered like a vast, shimmering tapestry. Classical physics describes one pattern, relativity describes another, and quantum theory reveals threads woven so tightly they defy ordinary language. The challenge is not that the pieces fail to fit, it's that our current tools are still too coarse, too early, too human. Yet this limitation is also a strange gift. It keeps the cosmos alive with potential, reminding us that progress is a continuous becoming, not a destination. Consider how many breakthroughs began with confusion, light behaving as both particle and wave, electrons occupying many states at once, empty space roiling with invisible energy. Each revelation seemed absurd at first, then gradually became foundational. That transformation mirrors how understanding unfolds in your own life, slowly, uneasily, then suddenly, all at once. The universe teaches in echoes, nudges, and paradoxes, never with the simplicity of a straight line. And though these concepts stretch imagination to its limits, they also bring you closer to the heart of what it means to exist at all. You are made of the very processes that defy comprehension. Your body is a constellation of particles that behave like waves. Your mind is a pattern arising from fields that flicker in and out of certainty. You are a walking reminder that quantum strangeness is not remote or abstract. It animates every second of your life. In moments of stillness, this perspective softens the boundaries of the self. The same forces that shape galaxies shape you. The same fluctuations that stir the vacuum stir your cells. The same uncertainty that governs electrons influences your thoughts, choices, and dreams. Instead of isolating you from the cosmos, the breakdown of reality draws you closer to it. You are not outside observing. You are inside participating. Seen from this angle, the mysteries of the tiny world feel less like puzzles and more like companions. They sit beside you without demanding resolution, offering quiet reminders that comprehension is not a prerequisite for peace. The universe doesn't hurry. It doesn't force its truths all at once. It unfolds in its own time, in its own way, trusting that curiosity will meet it halfway. If this quiet journey helped you unwind or offered you a gentle moment to breathe, I'm sincerely grateful you spent this time here with me. And if you feel like supporting this calm corner of the internet, feel free to leave a like and subscribe to the channel. It helps others find their way here. Before you drift off, let me know in the comments where you're watching from tonight and what time it is on your side of the world. Your presence, your curiosity, and even your silence matter more than you know. Like faint starlight crossing impossible distances, they reach far beyond this moment and illuminate the path forward, soft, steady, and beautifully mysterious.